Good morning, good afternoon, good evening, and welcome to AI for Good. My name is Bastian Kwas of the ITU, the International Telecommunication Union, and it's my privilege to introduce today's discussion, Algorithmic Recourse from Theory to Practice, by Professor Isabel Valera at the Computer Science Department at the University of Saarland. ITU is the United Nations Specialized Agency for Information and Communication Technologies, and also the organizer of AI for Good, together with 38 UN sister agencies and co-convened with Switzerland. For today's discussion, we'll be using the Q&A functionality that you can find at the bottom of your screen. Please post any questions that you would like to ask to our speaker today in the Q&A window. Additionally, there's the chat window, which you can use to communicate with other participants. Please make sure to send your message to all panelists and attendees so that everybody can see your message. You can select that just above the message box. And with that, it's now time for me to hand it over to our host today, Dr. Wojciech Samek, head of the AI department at Fraunhofer HHI and host of the Trustworthy AI series. Wojciech, over to you.
Yeah, thank you, Bastian. Yeah, I'm very happy to introduce our speaker today, Isabel Valera. She is a full professor on machine learning at the Department of Computer Science of University of Saarland in Saarbrücken in Germany, and an adjunct faculty at the Max Planck Institute for Software Systems in Saarbrücken. She's also a fellow of ALICE, where she is part of the robust machine learning program and of the Saarbrücken Artificial Intelligence and Machine Learning Unit. So I'm very happy to have you here today, Isabel. She's an expert in robust machine learning, interpretable machine learning, fair machine learning. So I very much look forward to your talk.
Hi, thank you very much for the nice introduction and also for inviting me to be here today. I'm gonna try to share now my slides. I hope you can see them fine. And as it was said before, I will, oops, sorry, I shared the wrong slides somehow. That is not what I wanted. I had them 1 second ago. Yeah, these ones. Sorry. Let me try again. Now, and as I was saying before, sorry for I guess I had too many presentations open at the same time. I will be talking today about algorithmic recourse, some theory about algorithmic recourse and how to go into practice. So for those that are not familiar with this concept, don't worry so much. I will definitely introduce the concept and also describe why it is important. So to give you a bit of context, we are going to focus today on machine learning algorithms that are used to inform or even replace human supervision in decision-making processes, which I call consequential because basically they make decisions about individuals and these decisions may have an impact in the life of the individuals that they decide about. You can imagine, or maybe you are familiar with these algorithms, for example, used in the US that are used to predict the risk of reoffending from individuals that are waiting for trial, as well as algorithms that are used for lending processes where they support decisions on whether to approve a loan or a credit, as well as hiring processes. And of course, you can imagine that in all these cases, the decision made by the algorithm may indeed have a consequence in the people's life. So the question, or one of the questions I try to address in my research is how do we make sure that the algorithms, machine learning algorithms that we design are aligned not only with human goals, for example, making as much profit for the bank as possible, but also with human values, that they are aligned with society and their ethics and values. So of course, if you think of the different stakeholders that are involved in the decision-making process, from the deployer to the justice system and regulators, all the way to the individuals that are affected by the decisions made by these algorithms, you can already see that they may have different questions or goals with regards to the algorithm. So for example, from the bank point of view, it might be important to see how to collect features, how to train the algorithm so that it is as accurate as possible and therefore profitable. From the justice system, we might be interested in seeing or understanding whether the algorithm fulfills our existing anti-discrimination laws. And from the point of view of the individual affected by the decision, they might be interested in understanding how the algorithm arrived to such a decision for them, and maybe even how they can revert an unfavorable decision. So this is basically the context where we are going to be today. And within all the ethical or the societal impact of machine learning, what I will be focusing today, or where algorithmic recourse actually lies in, is in the concept of interpretability, which, I mean, there are many ways in which interpretability has been defined in the literature. I took this definition from Doshi Velez and Bin Kim. And basically, they define it as the ability to explain or present in understandable terms to a human the outcome of an algorithm, in this case, for example, a decision or a prediction. For example, in the lending scenario that we had above, we have applicants with a set of features, which I usually divide into non-sensitive and sensitive features. This is only related with anti-discrimination laws and fairness, as we will see a bit later as well. And the goal is to predict whether each of these individuals will be able to repay or not the credit when granted. So in that particular case, how we are gonna achieve an interpretability, or what we are gonna focus, is in actually explaining how the algorithm arrived for each of these applicants to a particular decision. And the focus of this talk is gonna be the final individual, or the applicant, or user, it depends on the application, the application domain, how we call them, that is affected by the decision. So for example, in a lending situation, an individual that got a negative prediction and therefore didn't get the loan may wonder why didn't he or she get the loan, and what should they do in order to get the loan next time they apply. And in that context, a type of explanation that has been very used in the recent years, or very discussed in the recent years, would be a counterfactual explanation, and would be something of the form of, you were denied a loan because your salary was 25K. If your salary would have been 30K, you would have been granted the loan. So this is a type of explanation, counterfactual explanation, where they assume a counterfactual world, a hypothetical world, in which the applicant would have been in essence the same, but with some changes in their feature space. And they try to find, as we will see later, the most similar applicant to the current one, usually called the factual one, that would have gotten the loan. And it would be an applicant with the same set of features, but with a higher salary. So this is what we call a counterfactual explanation. And a related concept, which is the focus of this talk, it is what it is called algorithmic recourse. That doesn't focus only on explaining why the decision was made, as we just did with the counterfactual explanation, but how to transform this explanation into a sequence of actions, or into a process that the individual could act upon in order to get the loan, for example, in this case, next time they apply. So to be a bit more formal, how we have actually, in the literature, how we have actually formalized these two problems, have been as an optimization problem. And while in the case of the nearest counterfactual explanation, it is a counterfactual explanation, but we try to find the nearest or the most similar individual, in this case to the one that didn't get the loan, that would get the loan. So we have simply, in general, in the literature, formalized this as finding a new set of features at minimum distance or similarity, or as similar as possible to the factual one, which is this individual here, let's call him Edward, that would have gotten a different outcome in the binary case, loan accepted or rejected, than the one that he got, which was rejected. And we can, on the top of that, add some additional constraints, which I usually refer to as plausibility constraints, to, for example, ensure that this explanation, this new individual that we find, for example, lies in regions with high density values in terms of the data that was used to train the classifier. Here, there is the classifier. So graphically, imagine a very simple case where we have a classifier that says whether someone will repay or wouldn't repay the loan. We have our individual Edward here that didn't manage to repay the loan with two features, X1 and X2, that could be the salary and the savings. And the question would be, how do we find the most similar individual in terms of whatever similarity metric, for example, L0 or L1, that would have gotten the loan. But as I mentioned before, this gives us the most similar individual, but doesn't tell Edward how to actually go from here to here, and or what is the cost of that. So this is where the formulation of algorithmic recourse comes in. And as you can see here now, what in the initial literature by Ustun et al., they proposed was to minimize the cost of changing the set of features, where now we assume that the set of features can be changed in an additive way. So I can increase either my salary or my income or my savings or both of them by some value delta, such that the new set of features will go into a classification that would end up in this side of the boundary. And of course, you need to define the cost. So what is more costly, to increase your salary or to increase your savings? Or what is even plausible or feasible, what is actionable? Maybe I don't have the power to increase my salary, but only my savings. So in that regard, in addition to the plausibility constraints that I had before, we can add some additional feasibility constraints to simply account, for example, for the actionability of features. In the case of the salary, you can imagine I can ask my boss, in my case, the university, for an increase of salary, but if they say no, there's nothing I can really do, but maybe I can try to save. It's less costly for me to try to save a bit of more money per month, or maybe not, that depends on the particular situation. So this cost function is something that is individualized and we need to define. So something that it is a key assumption when we do this translation from counterfactual explanation to algorithmic recourse, or finding the actions that that the individual would need to perform, is that they are assuming that the new set of features obtained for recourse are after performing this action, would be the original set of features for the factual plus some delta vector, which is the shift on the feature value. So implicitly, what they are saying, and this is where we are talking about of the robustness of this formulation, is that these features, the features X1 and X2, salary and savings, actually can be manipulated in an independent way and be reduced or increased according to our plausible and feasible constraints. So in order to solve these two optimization problems, which might look here similar, but you can imagine that this here with this H theta can be any arbitrary machine learning algorithm that we have trained using a lot of data. So it can go from something simple like logistic regression to a very complex neural network. And it it's not as simple to solve in general these optimization problems. And this also explains why there is a bunch of literature, quite a bit of literature trying to find solutions for these two optimization problems I just saw before, and also working on the different constraints, how to incorporate different and realistic feasibility and plausibility constraints. But on the scope of the talk of today, I'm not going to directly enter in the different approaches that there exist. If you're interested, there are here 2 survey papers, one by my group, one from a group in, I believe, in Maryland, and with different scopes where you can have a look to the literature more or less up to date. But what I will focus today is on actually challenging the underlying assumption that exists when we have translated before the formulation, the optimization problem from counterfactual explanations to algorithmic recourse. And where we did this translation and assume that basically, if this is my classifier and these are my set of features, I can act on any feature independently of each other. And unfortunately, what we proved in our recent work is that these, I call them counterfactual explanation-based actions for recourse, only would guarantee that if acted upon, you get the desired outcome if the features that you have used to train your classifier are independent on each other. And as you can imagine, in general, that is not going to be the case. I've been talking about examples where we have a salary and we have a savings. And in general, you cannot assume that my ability of saving money doesn't depend on my salary, but precisely there is a causal relationship that says that I can save at most as much money as I have in my salary, or at least as I have in my income. So basically, what the actual world in general will look like is that while there is definitely a direct relationship from the features to the classifier, because we use them in the machine learning algorithm as inputs, in the actual world, the features that we use to input to the classifier are related with each other. And here, how these relationships are captured, I'm modeling them using a causal graph that basically says that X1 influences X2 and X3, and at the same time, X2 influences X3. So for example, my profession would influence my salary, and my salary would influence my profession would influence, for example, my savings. This is simply an example. So let's go a bit more in detail and show you an example. So it is well known that at least in the US, there are some statistics that say that on average, people seeking for a home or applying for loans, they tend to save 30% of their income per month in order to save for buying the house. So if we would model X1 as the salary or the income of the individuals, and X2 would be the savings. So in general, people have the savings that are per month that are 30% of their salary up to some random noise. Of course, not everybody saves exactly the same amount, but there is some noise. So if we make our example a bit more precise, let's imagine that Edward had a salary of 75K per year or per month, that depends, and managed to save 25K. And then we have a classifier, which is a very simple classifier, which depends on X1 and X2 minus some bias term. So what happens in this particular case is that if we assume an independent world, like the formulation of algorithmic recourse I saw at the beginning would do, basically it would say, well, what you need to do is to increase your savings from 25K to 30K by an increase, a delta of 5K. That is what it is saying. And that, if you would think of the causal world or in causal terms, what it would mean is that in our causal graph, which is shown in here on the top right, we would need to perform an intervention on X2 to break the relationship, the mechanism that relate X1 to X2 to fix the value of X2 to 30K. But of course, if you keep in mind and assuming that the cost of intervening on X1 and X2 would be the same, if you would keep in mind that there is a relationship between X1 and X2, a positive relationship, so the more income, the more savings I might be able to keep in mind to have, it is easy, it is easy to see that one could do better, at least in absolute terms, and by increasing only 14% your income, rather than increasing by 20% your savings, you would still ensure recourse. So in that case, everything that we are saying is that it might be worth asking your boss for a 14% increase in your salary before trying to compensate that in terms of your savings while keeping your salary possible. And as I said, that is assuming that the cost of intervening on your salary, your income and your savings is the same and both of them are feasible. But this is maybe just a naive example, but at the end of the day, what I'm trying to say is that if we want to find the set of actions that an individual would need to perform in order to change an unfavorable decision that applied to them, so in this case, in order to get the loan, we cannot assume that the features that enter the classifier are independent, but we need to account for the causal dependencies between them. So by using, rewriting our original optimization problem, we would still need to find the set of actions, so know how to change the features, but what interventions to apply into our causal model, where here we have the causal graph with the relationships, and we assume that we have some given functions that tell us how the causal relationships are exactly parametrically with respect to each other. And then when computing or solving this optimization problem, we would need to keep in mind that the new set of features will need to be computed in a causal way. Usually what we call this is a structural counterfactual, because basically you perform an intervention on this causal graph and then propagate the effect through the children. So for example, if I intervene in X1, this will have an effect on X2 and X3, and that I should account in order to find the set of actions with minimum cost in order for recourse. The good news with respect to this result is that the cost of this causal algorithmic recourse in this expression here is always going to be lower or equal than the one that we solved before. And also it will guarantee recourse. So if we can solve this optimization problem, we know that we have certainty under assuming that this structural causal model is known and the true one, that if we perform such actions, the ones recommended here, this A star, the individual will get the loan. This is the concept of causal algorithmic recourse in terms of helping people to revert an unfavorable from an unfavorable situation. And this also relates to the concept of fairness of algorithmic recourse, simply for the sake of completeness, where basically here we are talking about the cost or the effort that individuals need to place in order to change an unfavorable situation. And of course, this allows us to talk about discrimination or unfairness, as we want that disadvantaged groups or minority or protected social salient groups, there are many different ways in which we can call them. Those people that have historically been in a disadvantaged situation and therefore are less likely to get a favorable decision, don't need to spend even more effort and therefore being in an even more disadvantaged situation than for the advantaged group. So basically, this concept of algorithmic recourse, what basically they try is to, fairness in algorithmic recourse, is to equalize the effort that the people getting an unfavorable decision would need to do across different social salient groups based, for example, on gender or race. For example, in the case of the lending, something that usually happens, at least here in Germany, is that you are asked for some credit history or credit score. So here in Germany, they often apply the Schufa, it is called. And of course, when you come from as an immigrant, you don't have that history. So what you try to do is to find a decision-making process so that people that are already immigrant and they are in a kind of in general in a disadvantaged situation, they need to put more effort in order to get the credit. So for example, get 10 times more salary or savings and things like that. But of course, something that it is important here is that both for algorithmic recourse in terms of recommending people actions to overcome an unfavorable decision, but also in terms of training, algorithmic decision-making processes that are fair in terms of algorithmic recourse, we need to account for the causal dependencies between features, because this is the only way in which we can get a good estimate of what is the effort that people would really need to invest in order to change their situation. So simply for completeness, we have here our recourse formulation. This is the same as before, a bit more simplified, where we have the structural causal, the structural counterfactual, which is where the causality comes in. And fairness in causal algorithmic recourse can work at both the group and the individual level. And everything that they try is to equalize the effort that people would need to invest in order to get recourse. And of course, the problem that you may wonder is, I need to have causal dependencies. So can I warranty recourse even if my causal knowledge is imperfect or I don't have it? So unfortunately, we have a bit of bad news here, and recourse as well as fairness of recourse can only be guaranteed if the true causal model is known and fully specified. That means I really need not only the causal graph saying which variables, which features depend on which ones, but I also need to know what are the parametric form defining how these features are related, as well as the distributions of the noise. Of course, as a machine learner, the first thing that one thinks of is, well, I don't have these equations. I may have an idea of this graph, but I have data. So can I learn that from data? And unfortunately, and this is of course from the literature, if you're interested, I think Judea Pearl has a lot of work on that regard, and the group of Bernard Sholkoff as well. They have clearly shown that assumptions on the structural equations are usually unstable and impossible to unfalsify unless you have some knowledge and some particular type of data. So learning these functions from data, or at least from observational data, is in general not possible. So the question is, how can we achieve recourse or fairness in recourse, if you are more interested in the fairness side than on the explainability side, and their realistic assumptions? And this is where my group and I, we are moving in the recent months and say, well, Let's start with the strongest assumption that we have when we talk about causality, which are the structural equations. So let's assume that I don't have access to the structural equations, but I can get either from domain experts or from causal discovery tools, what are the causal relationship, parent-children relationship between my features. Is there anything I can do in terms of recourse? And the good news is that, yes, we can do something. But the bad news is that, oops, again. But the bad news is that, of course, you need to account for the uncertainty on these structural equations. And as I said, you can only guarantee recourse. So deterministically, you can say, if you do this, you will get what you want under the true perfect knowledge. So instead of the causal knowledge. So instead, what we can do is to get probabilistic algorithmic recourse, which would simply say, if you increase your salary by 14%, your savings are expected to grow proportionally, and as a consequence, you will get the loan approved with 90% probability. So we are moving from, if you make this, perform this action, you will get what you want, to more of kind of a confident type of interval where you say, well, if you perform that action with that and keep performing the rest as it is, with whatever probability you will get what you are seeking for. So, of course, how we can relax these assumptions and how we can compute this probability is a bit of a challenge. But in my group so far, we have been thinking of how to relax these assumptions and propose different solutions. And our first solution that we could come up with was to say, well, what if I assume I have the causal graph? I have causal sufficiency. That simply means that there are no hidden confounders, or that the noise variables, these use I had in the previous slide, are independent for all the variables. And our main assumption here would be, I don't know what are the parametric form of F1, F2, and F3, but I know that they are affected by Gaussian noise, so U's are Gaussian, and they affect them in an additive manner. So in that particular case, I can use a Gaussian process prior to estimate the counterfactual distribution by averaging over an infinite number of structural equations of these functions F1, F2, and F3 that we model using the Gaussian process. But of course, the question here would be, well, is it really my income and my savings for the population having a Gaussian distribution? Or even worse, when I have some features, like for example, my age or my profession, where they are definitely no Gaussian, what can I do? Which in this kind of decision-making processes is quite common. So in that case, the best we could come up with was, well, we can assume the causal graph, we can assume causal sufficiency, and no assumptions at all on the structural equation, including the noise. But in that particular case, we unfortunately would need to move away from the counterfactual reasoning proposed by Baer, which is usually called the range 3, all the way to the interventional or range 2 of causal reasoning, which doesn't directly argue at the level of the individual, but it argues more at the level of a subpopulation. So to give you an intuition, in here, what I'm saying, okay, if Edward performs a set of actions because of my uncertainty on the structural equations, I don't know exactly where I will end up, but I have an intuition of, or at least a confident interval or a region where I know I will end up. And of course, the more I move this cloud to the positive side, the more certain I am, but of course, in general, the more effort. In the case of the second approach, which works at the subpopulation level, what we can do is that how much or what are the actions that Edward and similar individuals to Edward would need to perform in order to jump to the positive side. So we are not arguing about counterfactuals, but on interventions on people that are similar to Edward. And similar, of course, we need to define what means, as we did in counterfactual explanations. So in that regard, just to be a bit more formal, if we go into probabilistic and individualized recourse, we need to assume here that we have additive Gaussian noise. So this is our main assumption. And then we can basically model our structural equations using a Gaussian process. In that particular case, basically, we could replicate similar steps like the abduction, action, and prediction steps for computing counterfactuals, for those familiar with the counterfactual literature. And the only thing is that we will need to perform them with respect to the Gaussian process. And of course, what we will have is the same optimization problem as before, where we try to find a set of actions that minimize the cost or the effort. But now we need to have an expectation, so it is not deterministic, our structural counterfactual, where we have a distribution on where this structural counterfactual may end up. And this is where the probability comes from. And we try to make that greater than a threshold that kind of says how certain we want to be, or how much probability mass we want from this cloud to be on the positive side. So basically, you can set this threshold so that it trades off the cost and the validity, in the sense of how likely it is that you end up in the other side of the boundary, in the positive prediction, when performing an action. This is for the individualized one. And as I said, for the subpopulation based, for which we use simply a variation autoencoder, we basically need to work at the population level. And basically, we simply estimate the effect of an action in a subpopulation similar to the factual individual. And basically here, this expectation is computed over such a subpopulation. So it is called interventional distribution. But everything I'm trying to say is that basically, when you try to further relax your assumptions, you have more uncertainty that you need to capture. And that in general, if you want to keep the same uncertainty or the same certainty of getting the favorable prediction, you will need to invest more effort. And here, when we measure validity, is simply because it is a toy example with the true causal model. And we say, well, for those actions that we recommended, which percentage of these actions recommended would bring you to the favorable decision under the true causal model. And of course, the more you increase your threshold, the more you go towards 100%. And of course, you do that more if your causal assumptions hold and you work at the individual level. However, if your causal assumptions don't hold, you might believe that this set of actions will take you to where you wanted to go, but you don't have any certainty. So there is always this trade-off between the cost and the validity, and therefore between the individual level and the subpopulation level, but how much I can relax or be certain about my causal assumptions. So simply in summary, I think probably if you are familiar with explainability literature, you may have heard before today about counterfactual explanations. Unfortunately, if there is something that I think we overdid it in the literature, was to say, well, counterfactual explanations directly translate into actions for recourse. And I hope after this talk, it is clear for all of you that that is not the case. And in general, these explanations of I would have needed to have a higher salary don't translate into the fact that if my salary is higher, I will get the favorable decision. Something that we also saw is that for recourse, or for finding these actions, which is kind of the ultimate goal of giving an explanation to an individual, we need causal knowledge. And unfortunately, in order to get theoretical guarantees or deterministic warranties, we really need perfect causal knowledge. But this is in general not possible. I haven't seen any case in practice where we have perfect causal knowledge in these kind of settings. And that means we are gonna need, if we wanna get close to good actions to recommend to individuals, we need to relax these assumptions. But of course, relaxing these assumptions come at the cost of going from deterministic or with warranties to probabilistic approaches. So this is something we need to still investigate from the psychological point of view, whether these kind of explanations or actions for recourse would be useful for individuals. So as for the way to go, I mentioned here a couple of approaches on how to relax these assumptions, but these are only very minor assumptions that I relax. There are many others in causal reasoning, and it is unclear how to relax them and how far we can go. This is from the technical point of view. From the application point of view, it is very unclear how to bring algorithmic recourse into practice. We know this is a desirable property from any explanation method, but it is not very clear how to bring that in practice, or even if this approach of probabilistic recourse, as I just saw, it is a proper and practical solution that would be accepted by the users or by the regulators even. And of course, at the end of the day, everything boils down to when we try to explain machine learning algorithms, what type of explanations can we give or are useful to give to individuals? And this is something for which we still have more questions than answers. I still believe that the more we go into details, the more we learn or the more we know that we don't know. But if something I hope comes out of this talk is that in this particular scenario, we have talked about algorithmic recourse and fairness of algorithmic recourse. And I said, hey, look at this list of papers from the survey, all of them trying to tackle somehow these problems. But they all have the same technical assumption that doesn't guarantee anything. So they were asking for even too much or useless effort to individuals to change an unfavorable situation. And this was simply because we were not very explicit or careful with our assumptions. So in general, something I have learned over the years is that whenever we talk about fairness or interpretability or even robustness, very often the problems that I encounter come from the assumptions that we implicitly make and are not directly explicit, and then they come at a very high societal cost in terms of, for example, unfairness. So please try to be as explicit as possible with the assumptions when you design your algorithms, either for the algorithm to decide, for the algorithm to explain, for the algorithm to correct for fairness, for the algorithm to account for robustness, privacy, so on and so forth. And with that, I'm very thankful for your time, and I'm very happy to take any questions. Thank you.
Thank you very much, Isabel. Very interesting talk. So I see some questions from the audience. So maybe we can start with the question from Stefano. Can you achieve a recourse using adversarial techniques? Manipulating the input under some distance constraint, you can probably find a good recourse example.
Yes and no. So I think you can find that would bring you to solutions on the counterfactual explanations. But the problem is, how can you manipulate and know what are the downstream effects of the manipulating one feature on a different one without the causal knowledge? So if you have causal knowledge, then definitely adversarial. So let me try to go a bit behind. So in this plot. So for example, I can try to manipulate X1. If I know the causal model, I can see the effect on X2 and X3, and definitely solving the optimization problem can be done via adversarial example. There are many ways in which I can solve the optimization problem. The problem in general doesn't come from solving the optimization problem. The problem comes from how I know how X1 exactly affects X2 and X3 and so on, only from observational data. This is what the challenge is. Otherwise, I will still be in the counterfactual explanation side. So if you would have been like this, you would have gotten the loan, but not directly apply into actions for recourse. I hope I managed to convey the message.
Mm-hmm. Another question, so causal models are often mentioned in the context of robustness against domain shifts. In their NIPS 2021 paper on robust recourse, Lacarayu and co-authors propose ROA and compare it to your 2021 facts approach. Can causal algorithmic recourse be expected to be robust to domain or model shifts, provided the causal assumptions are correct?
Yeah, so if causal assumptions are correct, right?
Yes.
Based on that, definitely everything boils down to how you solve the optimization problem. And I strongly believe that for solving the optimization problem, I mean, for example, something that looks like this or differently, probably there are many better ways of solving that optimization problem than the ones we apply in this paper, which was not the focus. Our focus was not that much on the optimization problem, but more on the warranties or how we can account for uncertainty. The problem comes when your causal assumptions you're uncertain, or there is a mismatch. And there is where definitely we need to see, for example, like small shifts in your equations might break down everything, or if you think that your noise is additive but it is not, everything again changes. So in that particular case, I think it's safer to go for more of a probabilistic approach and reduce the causal assumptions or relax them.
We have another question to your work. So your work seems to be based on inputs that are continuous variables. What if the inputs are different form, like images skimmed from the applicant's social media?
So as for, here, they don't need to be continuous directly. It is true that everything becomes, in terms of formulation, easier when they are continuous. What I'm assuming is that, for example, here an X1 would be a whole image. So it doesn't make sense to divide pixel by pixel. In that case, definitely when the variables are, for example, multidimensional, or where they are categorical, or any other type like ordinal, the optimization problem becomes harder. And this is definitely something we are looking at. But getting the optimization pipeline in this, let's say, not as differentiable or as homogeneous settings make the optimization problem harder. And probably there are very interesting solutions in order for that, because there are previous work with regard to these kind of problems without the causal part on several of the papers in these surveys.
Mm-hmm. So I have also like a question. So like, do you see any links like from this work to works, for example, in game theory? I mean, what happens if things change in your approach, if the cost function changes, or if this causality structure changes? Can we interpret? Would it be then fit? Like, would game theory be a tool to go, or how do you see the relationship?
So I think, I have some assumptions I haven't talked about explicitly. And the main assumption is that I'm assuming stationary distributions, meaning I'm assuming that this structural causal model is fixed and the distributions are stationary. And known, less, or well known, or better known. Definitely changing the cost function, it is possible, and I think it's a good exercise to try different cost functions to provide different set of actions to individual, and that wouldn't break the whole framework as long as you can solve the optimization problem. If you would break the stationarity, for example, because of the strategic behavior of people reacting to your algorithm, for example, I give you recommendations of what you need to do. So next applicants, they know how the thing works, and they apply what it is usually called strategic behavior. In that case, definitely you would need to correct for that. And I'm aware that at least without the causal framework, there has been several approaches proposed to at least to do, for example, counterfactual explanations. Not that sure about algorithmic recourse. Several of them based on game theory, but there are other approaches that account for that, so that the algorithm is designed in a way that it is robust to these small shifts in the population due to strategic behavior. Definitely more non-stationary cases where you don't have any control on how the underlying distribution changes will break not only my explanation method, but will also break the classifiers, right? Because usually classifiers are assumed to be trained for the population they are going to be applied. So I guess that would be interesting, but definitely would need to enter more in an online type of pipeline, I guess.
So do we have any other questions? So another desiderata for recourse is to provide a diverse set of counterfactuals. Is this still achievable in the context of causal recourse?
I believe so. So in the sense that you can be, so looking at this optimization problem, right, you can play with the plausibility and the feasibility constraints. You could also say, well, give me another set of actions that is not the one that you have proposed in the previous iteration. That would be an additional constraint. You can play with the cost function. There are many different ways in which you can change the problem to explore different or diverse solutions, like it has been done in the counterfactual explanation. That is definitely and potentially interesting. Also, something that I think is missing a bit from the algorithmic recourse work, but also for the counterfactual explanation work, is a bit with regard to this cost function or this similarity function that we had before, right? How do we define them? What is a realistic cost function? Can we make it a bit interactive with the user? Can the user set a cost function that is not directly numerical, but simply say, hey, acting on X1 is more costly for me than on X2, but I cannot tell you by how much more, right? Or because and this brings me back to one of my last comments, which is, how do we make this to be not only a mathematical game for us, but how do we bring that to the user? How do we make this suitable for deployment and useful for users?
Yes, I think that's a very, very important direction. So I have a last one. So what is the computational complexity of all this, and how this, I mean, how the complexity of the model kicks in? So can you use this for very complex models, or so maybe you can say a bit about that?
Well, so it has two parts, definitely. So definitely the classifier for both counterfactual explanations and recourse. If you have a highly nonlinear, for example, decision boundary, that makes things difficult in general in terms of optimization to get warranties. The same happens with the distance or the cost function. So that is something where I think the literature has done quite some effort in saying, well, you can have it fast, but maybe not with warranties, and then you go to gradient-based approaches and assume cost functions and classifiers that are differentiable. Or you can try to have some warranties. For example, my group and I, we work on counterfactual explanations using formal verification, where we get some warranties on the optimality of the solution. So that is on one side. And again, warranties are usually paid at the price of complexity. In terms of counterfactuals, if you have the structural causal model and you can follow the prediction action, abduction, prediction, action steps by pair, that is in general easy because it's almost deterministic. If it is not deterministic, then you have Monte Carlo approaches, or in our case, Gaussian processes or VAEs. That makes the complexity quite interesting, right? Because you really need to, at least the learning, once you have learned the VAE or the Gaussian process, inference time is cheap. And the cost part comes on the optimization problem for every individual, but you need to have learned a proper probabilistic model, which is in general expensive. So definitely relaxing assumptions, solving the optimization problem with warranties usually comes with complexity or computational complexity. And this is also something that we are tackling at how do we find practical solutions with as much warranties as possible while efficient in terms of data and also in terms of computational complexity is definitely also something worth looking at.
Mm-hmm. Okay, so Isabel, thank you very much for accepting this invitation and for giving this amazing talk. So yeah, thanks a lot also for the audience, for the good discussion, and yeah, see you all next time.
Thank you very much for the invitation and listening to me. Bye.
Thank you, Wojciech, and a big thanks also to Isabel for our very interesting discussion today. We hope that you enjoyed the webinar, and we are launching a quick poll that will be coming up on your screen now. And in the meantime, let me mention a few things that may be of interest to you. So next Thursday, 7 December at 8 a.m. European time, we have part 2 of a series that started this morning at 8 o'clock. Standardization, ensuring trustworthy digital society enabled by AI technology. So the second part of that will be taking place next Thursday, and it features, among other speakers, the host of the Trustworthy AI series, Wojciech Samek, head of the AI department at Fraunhofer Heinrich Hertz Institute, and other distinguished speakers. We are posting the information for this in the chat. Additionally, we have upcoming sessions in the Trustworthy AI series that you can also find in the chat. And with that, I'd like to once again thank everybody, our speaker, Isabel, our host, Wojciech, your participants, our partners, sponsors, and co-conveners, Switzerland, and we hope to see you soon.
Rewind selector, rewind selector, rewind selector. Rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector. Rewind selector, rewind selector, rewind selector. selector. Rewind selector. Rewind selector. Rewind selector. Rewind selector. Rewind selector.